Hi everyone, my name is Kagwa and Treasure. Welcome to my YouTube channel. In this video, I'm going to present that project called the Multimodal Edge AI Partial Discharge Diagnostic System. In the development of this project, I designed two machine learning models, and in this video, I'm going to explain the models. So the contents of this presentation include the dataset description, the model architecture and explanation of both these models, the results, the conclusions, the limitations, and any acknowledgements. So the data description, I used a data set that consisted of 8,646 wave files, audio files that were grouped into 2,882 partial discharge, sharp and white Gaussian audio files. These are the sounds that are produced by electrical equipment. So each audio file was sampled as 96 kilohertz, had a duration of 50 seconds, and within these files, there were repeated segments of 10 seconds of each sound being played. So each sound was played 5 times in each of these files. So the data was collected across the 94 locations on 18 SATA calls using a 32-channel MEMS microphone, and this information is captured in the naming of these files, as you can see. So we have the fault location number, the audio file type, and the white Gaussian noise. So the first model I'm going to explain is the PD neural symbolic model, whereby this model was informed by two sources of knowledge. The first source of knowledge is the neural perception, then the physics knowledge. So with the neural perception, here we have the three-dimensional convolutional neural networks that learns patterns from the acoustic kilograms that have been derived from the data set, and we have the physics knowledge that is informed by the processed physical descriptors of the audio. So we have the input being an acoustic scalogram, the scalogram being like an image of the wave, and this is the shape of the scalogram, which shows that it's 32 channels, the frequency resolution, and the temporal resolution. And we have the physics features that were incorporated into this model included the rise. The rise is how high the signal rises. The kurtosis is the different peaks, the rate at which the signal changes, which means how many peaks the peaks a signal has. The centroid is where the energy is most concentrated, and you have the skew that represents the shape of the waveform of the different audio signals. So these were calculated for each file, and then they were stored in a physics vector that was fed into our model. So this is an example of how a scalogram looks like. This was the image that was fed into the CNN that we trained. So the first branch was the neuroperception branch that consisted of 4 residual blocks. Each residual block had 2 3D convolutional layers with a kernel size of 3 times 3 kernels, which is roughly 27 kernels. And then we had the default stride of 1, which means that the output stays the same as the input, and also had a padding of 1, which means that the spaces were added at the edges of the images that were fed into the CNN in order to prevent the data loss, especially on the edges. That's why we add padding. So after the convolutional layer, we had the batch normalization. Normalization, what it does is that it normalizes the batched data. So it normalizes, which means it makes the values uniform across the data in order to prevent the data stats or the statistics of the data from changing rapidly during training, which may slow down the learning, whereby you can have we have one data point that has a very high value, and other data point has a very low value. So if they're in the same range, that is normalization, it prevents that. And then we have after normalization, we end up with a squeeze excitation squeeze excitation attention block. What this block does, it emphasizes the important features that were derived from the two previous layers. So it adds attention to those features so that the model can pay more attention to the features. And then we have, after batch normalization, we added a skip connection that can resizes the input to match the output shape if there was a mismatch between the input and the output shape, or if the stride was not equal to 1. So if the stride is like equal to 2, it means that the output may change or it may reduce. And then otherwise, it passes the input as it is. So with the squeeze excitation block, how it works. So we have the squeeze. The first layer is the squeeze layer, whereby it uses the 3D adaptive average pooling layer. It reduces the input spatial dimensions by averaging, hence summarizing the 3D volume in order to capture the global information. So it squeezes down the 3D volume, the 3D volume, and then it captures the global information. We have excitation that consists of 2 linear layers, whereby the first layer will compress the input, focus on essential features, followed by the ReLU layer. The ReLU layer, what it does, it activates. It's used in activation, whereby it removes the negative values and puts them at 0. So it turns negative values to 0 and it keeps the positive values. This adds nonlinearity to our model in order to improve its learning, so that you can like master curves in the data. So it doesn't assume that the data is linear. So that's what the ReLU does. And then it's a regularized linear unit in full. So from then the weights are then taken to a sigmoid layer, which can put them in a range of 0 to 1. So these weights are then multiplied with the features or the numbers. And for example, if a feature has a weight of 1, it stays as it is, and if it has a weight of 0, it can be removed. That's attention. So it's a range of 0 to 1. You can have 1.5, 0.9. So different features can get different weight attentions. So next is a forward pass. This is how the data flows in the residual block. So you have the input, which is a scalegram. It is passed through the skip connection, and first the input is first saved as an identity, and then it is passed through the convolutional layers. It's then normalized, and then attention is applied to it in order to focus on more useful features. Then at the end, the input will then be added to the processed data. The saved identity that you saved initially will be added to the processed data. So this skips the convolutions if they were not useful. And finally, the ReLU is applied to activate the combined features. So the identity, it's in case the convolutions did not produce any useful features, that the data is returned as it is. It is still saved as the identity and is added to the processed X. So the full model explanation, we see that the physics branch also processes the full features, and then it expands them to the 32 hidden units in the linear layer. We have the ReLU adding the nonlinearity. We have batch normalization, which normalizes the feature. The second layer refines these features, and we have the dropout, which can turns off the 30% of the neurons, and the branch produces a 32 vector embedding. So as you can see, the fusion layer combines the neural and the physics features to form the final prediction. So I have the neural layer, the physics, the neural having 256, and then the physical output was 32. So it combines them to form 288 features. Then in the linear layer, this output will be fused to 128 features. The ReLU will add the nonlinearity, and then when we reach the final linear layer, these features will be reduced into the 3 class scores after training and going through each of these steps, which is the linear, the regularization, normalization, dropout. So at the end, we have 3 class scores. So this is the example of the architecture. As you can see, we have the scaleogram input. So we have the scaleogram input here, the scaleogram, and then it goes through each of these blocks, the 4 residual blocks, then goes to the average pooling, then it's flattened. So before the linear layer, we must first flatten the features. So you can have a three-dimensional feature will be flattened into a one-dimensional array, and then it's fed to the linear layer. So at this stage, we see that it's where the physics features are added. So they are concatenated and then put in the fusion layer, and then the 3 classes are produced. So this is the residual block, whereby we have an input tensor. So the branch is where the identity is saved. So we have the branch which is the skip connection, and then we have the convolutional path, and then we have the attention, the attention block, the squeeze excitation block, which outputs the weights, and the weights are then applied on these features to scale them or to reduce them or to remove some of them according to attention that has been calculated from this attention block. And then the features are then concatenated, and then they're activated, and then you get an output tensor, which is fed across these layers. So we have the learning and optimization. So the model learns through the forward pass, whereby the model takes the input and predicts the class scores. Then we have the loss calculation via the cross entropy loss. Back propagation, this loss is traced through, whereby as training happens, you'll get a loss, and this loss is traced through the layers to see which weight contributed to the loss, and then this weight is updated in order to reduce the feature errors. That's how the model learns. We have optimization using the Adam optimizer with weight decay. When you add weight decay, it reduces the overfitting, and it adapts the learning per parameter, the learning rate per parameter. And then we have the reduce on plateau, which reduces the learning rate in case the validation error plateaus. If you have the same validation error across a number of epochs, this is where the reduce on learning rate on plateau scheduler comes in. So we have the learning and optimization, the features that were optimized, the parameters. We have the convolutional kernels, we have the linear layer weights, the batch normalization weights, attention parameters. And then we have hyperparameters that are also adjusted. We have the learning rates, the weight decay, the number of the epochs, which means the number of times the number of cycles the model trains, the scheduler patience, how long are we going to wait before we update the learning rate, and then the early stopping patience, which means that how many epochs are we going to implement early stopping, whereby the setup performance stays the same. This is to prevent overfitting. So these were the output results and discussions. So you can see that we were able to get a train accuracy of 98% and validation accuracy of 95%. As you can see on these graphs, there is minimal overfitting or underfitting, and the lines for validation and train are close to each other. And then we see here, so where the grad comes in for explainable AI. So this shows how the scaleogram, the CNN sees the scaleogram. After the CNN has inputted the scaleogram, and this shows the areas in the scaleogram that inform the model results. So it shows where the model attention was mainly. So you can see it was mainly at the beginning of the left of the scaleogram. So then the second model I trained was the PD localization model. The purpose of this model was to estimate the spatial location of the partial discharge source from the acoustic data. So this model contained 3 major components. We had the CNN feature extractor, the physics feature network, and the fusion regression head. So that's the input was an acoustic scaleogram, and then there was also the physics features of rise, characteristics, centroid, and skew. So with the CNN extractor, it consisted of 3 convolutional blocks. The first convolutional block was to detect the low-level acoustic features. It took an output of 32. It outputted a feature map of 64 features using a 3x3 kernel. Then we had the ReLU to add the nonlinearity. We had the maximum pool 2D that captures the most important features and reduces the spatial dimension. And then we had the second convolutional layer, which would learn the complex spatial patterns. It will take the input of the 64 feature map, and then it outputs a feature map of 128 features using a 3x3 kernel. So we had the ReLU coming in and also the maximum pooling. The same for the third convolutional layer. We had the ReLU coming in and then the adaptive average pooling that flattened the spatial dimensions. So the second branch was the physics feature branch, which processed the physics features. There were 4 features, which was the rise, characteristics, and centroid, and skew. So the input was 4 features, then the output was as 64 dimensional representations from the raw physics data. So this physics data informs training. Since we are to employ this model in an environment that is highly informed by physics, it's best that we also include this physics data in the training of the model. So we had the feature fusion, whereby the output of the 2 branches are combined with using feature concatenation to form a 320 dimensional vector. So with the third branch was the regression head. The regression head, it consisted of a fusion vector that is passed through a fully connected regression network that consists of 3 linear layers. So we had the linear layer 1 that reduces the feature from the 320 to 128 features. We have the ReLU that adds the non-linearity. We had the dropout. We had the linear layer, and the third linear layer finally reduces the layers from 64 to 2 local coordinates. So how the model learned, it was trained with supervised learning. There was a forward pass where the input is forwarded through the network to produce the spatial coordinates of the fault location. There was loss computation, which was done using the mean squared error, and there was back propagation, which I had explained earlier. So this is the model architecture. As you can see here, we have the CNN branch, we have the physics network branch, and all of this is merged into the fusion and localization head, which outputs these XY coordinates. With these coordinates, we're able to compute the location of the fault. So we have the learning and optimization. So the models that we optimize were the convolutional kernels and then the linear layer weights. So we had the hyperparameters that we optimized. We have the learning rate and also the epochs that were also optimized. So optimization was also done with the Adam, which adapts the learning rate per parameter. It also involves a weight decay. That's why it's Adam W. So these were the output results. We had the best results occurring at epoch 28 and having a mean localization error of around 4.02, which means that the model was 4 units away from the true value. So the conclusions and limitations, we have a conclusion whereby both models achieved acceptable results, though further improvement can be achieved on the localization model. Have limitations such as the computing power. They had a large data set, so over 32 GB, that prolonged the processing time. The next step will be further model improvement and testing on unseen data. And then I acknowledge in this process, I acknowledge Mr. Galiwango, our lecturer, for his teachings on machine learning that have influenced the development of this work. Thank you so much and have a nice day.